pleasure to be able to speak at this wonderful event. And I, of course, want to thank all the organizers, and particularly Charlie, who's done. And particularly, I'd like to thank Charlie, not only for the invitation, but for the wonderful historical work she's done in connection with Segre and his school. My contribution here will be very minimal in a way, but it's of course a well-known theme that in the history of geometry, that there's a national shift in a way that we've alluded to many places, that Germany and the school of Klepsch and so forth is a very important place, and somehow the momentum moves over to Italy, and the last talk, of course, touched on many elements involved in the Italian National School and so forth. So I'm talking about a very specific sort of thing involving Klein and involving Segre and so forth at the very beginning of Segre's career. And it also involves Gino Loria. So it's the very first paper that they published in Matematica G together, and it deals with the theory of quadratic line complexes, a topic that Felix Klein learned in his youth from Brucker. So this was written together with Gino Loria, and it was submitted to Klein in 1883 for publication in Matematica G. And these two papers, actually, which I'll be talking about today, together with Segre's published dissertation, really move around topics that Felix Klein had dealt with 10 years earlier in his own work. These, of course, are the two publications. The first part of Segre's dissertation really deals with hyperspace theory, and the interesting and lesser-known element is how he applies it to the classification of quadratic line complexes, and that's the topic I'm touching on here today. So the first of these papers appears a little bit earlier with Loria and deals with a special type of quadratic line complex, a so-called harmonic complex introduced by Battellini actually in 1886, and I'll tell a little bit of that story. And interestingly enough, thanks to the publication, recent publication by Erika Luciano and Silvia Roero of the correspondence of Segre, we can actually see how the second paper came about after the first. And so this is a really very nice opportunity to get into this story. Of course, Loria, like Segre, had studied here in Turin with Enrico Dovidio, and his topic was actually a topic in quadratic line complexes, a well-known special type called the tetrahedral line complex. And of course, as a historian of mathematics, I cannot neglect, that Loria goes on to become a very, very distinguished historian himself. And this is perhaps significant too, how many of these people we just heard about Coolidge, who himself in his later years becomes a rather distinguished historian of mathematics. So there's a real sensitivity for the history of geometry that's taking place here among these figures in Segre's network. In his obituary for Segre, published in the Jahresbericht der Deutschen Mathematikervereinigung, his student Alessandro Taricini had this to say about this early work. Segre's entire early work was connected with Klein's researches on quadratic line complexes. And yet, it clearly differed from these. On the one hand, through its quite different and more skillful classification, as well as through its introduction of fruitful new concepts. On the other, through the broader generality of its results and the careful treatment of special cases. And it's this last part that I really want to stress here. I think the methodological differences are fairly well known, but the care with which Segre went about analyzing these special cases is really quite remarkable. So as I said, this comes out in letters that were recently published in the Politecnico 2012. You see the reference here. And all of these letters, I mean, I haven't had a chance myself to study them in enough detail. They're a very, very rich source and a very important documentation for the history of geometry, and they shed a lot of light on what was happening in this time period and thereafter. The very first letter is written by both of them, Segre and Loria, accompanying the manuscript that they submit and so forth, and they explain, of course, the motivation behind their work, and there's an Italian story to this, really, that's quite interesting. It's complicated, so I'm only going to, of course, be very vague here in 30 minutes. It would take, several lectures to actually get into the details of this, but in effect, they studied 23 special cases of these so-called harmonic quadratic line complexes, and they mainly go after this by looking at the singularity surfaces associated with these things, which are typically then quartic surfaces of various types. And in the letter, they call attention to how rich the geometry here is, so they talk about some of the special cases, just some that come up. Cayley's tetrahedroid is about the most general case that comes up, and you have Steiner's Roman surface, certain of the ruled quartic surfaces that Cremona had studied, cubic surface of Schläfli and others. And the story here begins really with Bartolini, who published in 1866 a first study of a classification of these so-called harmonic complexes, but Ascieri is the one who actually detects their significance, and then there are a few papers written in between afterward, and in the letter they cite the work of Dabu, Weiler, and Hurst dealing with special cases, but just special cases. They are the first to do a systematic study of these things. Now I'll go back to a few of these things to explain it a little better, but I think since the topic of quadratic line complexes is not very modern and it's quite obscure, I'll just say a few things as background information about where it came from, the history of this topic, and why it was so important to people like Klein. It's usual to attribute the beginning of this theory to Plucker, and probably for good reason. He's the first to really make it into a general type of analysis and so forth, and to look at algebraic systems of lines defined by a homogeneous algebraic equation in line coordinates as a topic to study systematically. So the notion of a general line complex is introduced by Plucker. He brings it into play in his earlier work a little bit, but it really is in the 1860s that the theory begins. So here are just a couple of technicalities that are probably easy enough to understand, and of course they're well known to algebraic geometers. If you just take 2 points in homogeneous coordinates in 3 space, then you can from them form 6 determinants, and these are the so-called Plucker coordinates that you get, even though he was surely not the first to come up with them, as Segre pointed out to Klein. Their significance here is they satisfy a quadratic identity, that's this capital P that appears here. And so you can then look at these coordinates as, of course, they're associated with lines, but the lines, in effect, satisfy this quadratic relation. It's important when talking about Plucker to realize that there's a whole bunch of algebra that kicks in right away after he dies, and he's pretty much out of the loop when it comes to modern invariant theory and the types of work that are done afterward. So his stuff is not very readable, and it was quickly forgotten, but he nevertheless had a clear idea of what he was after, and he was very much interested in the geometry of these objects, as I'll try to show in a little bit, the types of singularity surfaces that come up in quadratic line complexes. So the line complex is then defined by this additional relation, omega. We're looking at the quadratic case, which is already very rich, and so that keeps people busy. The somewhat more elegant way to go and more powerful way to go was discovered by Klein after Plücker's death, and he introduced what are today called Kleinian coordinates by diagonalizing then these forms. And so you can then look at the same type of object where then in the x coordinates it's just a sum of squares equal to 0, and you get different cases then for the omegas depending on the eigenvalues of the coefficients in the other quadratic form. Already early on, Klein also noticed this Italian point of view, namely it's more elegant and powerful to actually put everything in the context of projective 5 space and look at then the lines in space as a quadratic surface in this space, and he wrote about this in 1872, and of course this was one of the things that profoundly influenced Segre, but I would emphasize that neither Klein or any of his students really goes after this and exploits this idea. That Segre is the first to really do that and to make even this special case of line geometry part of hyperspace theory. So that's in the 1880s, of course. What's remarkable about Klein's early career is when you just think about how quickly he comes in touch with key figures in the earlier period. He was a student of Plücker in Bonn in the 1860s. Plücker died in 1868, so Klein had to actually edit his book on line geometry, which came out then after Plücker's death. Then he moves into the circles around Klepsch in Göttingen. He meets Sophus Lie shortly after that in Berlin, and they are in Kummer's seminar together, and Kummer is himself a key figure in the history of this subject. So Klein was somehow in the right place at the right time and learned a lot of these things. This is Alfred Klepsch, who you see also died very young. So you have a kind of strange situation that Klein lost his two mentors within 4 years. And at the time Klepsch died, Klein had just moved on to Erlangen as professor there. So this, of course, put him in a very prominent position in Germany. Partly explains, I think, too, why line geometry and these early things he worked on become less important for him, because he's training all kinds of people doing different things, and so he moves away from that topic. And of course, Lie has to be brought into the story too, and if you look at Lie's early work, it's heavily loaded with line geometry, sphere geometry, and so on, and so he's a big part of this story as well. The geometries, I've shown you what the algebra looks like. The geometry of a line complex is at least intuitively simple to understand, because at each point in space you've got lines that pass through it, and in a quadratic line complex, those generic points then will determine a cone. And you can then look at the thing dually as well. You can look at a generic plane in space, and that will then give you a line conic. It will give you then an envelope of lines, give you a conic in the generic case. But the singularity surface here is really the key thing. What happens when it's not a generic point or a generic plane, and then those line structures collapse to degenerate cases. So then you're looking at a cone which then collapses into two planes or two pencils of lines, or you're looking at a plane in which you get two pencils of lines in that. And then that set of points, that set of degenerate points, gives you your singularity surface, which is typically a quartic surface. So this whole theory centers around a very new and difficult topic, the structure of special types of quartic surfaces. And it began not in this special context, but it began actually earlier with Kummer in his work on ray systems. And these, of course, have the maximum number of singularities, these Kummer surfaces, 16. So you have a configuration of 16 singular points in 16 singular planes, and they form a special 16-6 configuration in space. So this is what a model of a typical Kummer surface looks like here, where you have a central tetrahedron, and around that tetrahedron then you have 4 others, and then these things going off to infinity projectively are just the 2 pieces of the other tetrahedra, so you have 3 additional things going off to infinity for a total of 8 of these things. So that would be in, you know, the special symmetric case, etc. But that's sort of a starting point that Kummer developed, and the context in line geometry was discovered by Klein. As I say, these are singularity surfaces, and he discovered that in the generic case of a quadratic line complex, you have a 1-parameter system of these things which have these singularity surfaces of that type. So that's the most generic type of quartic surface that you get. I give here 2 examples of really trivial or simple cases, just to give the flavor of the subject. So when you're thinking about the most primitive type of example of a quadratic line complex, you can just take a quadric surface in space and look at its tangents, and that tangent structure will in fact give you a 9-parameter system, because that's how many parameters you need for the quadric surface. And the singularity surface there just collapses to the tangent planes. So you have cones outside it, but then otherwise you have tangent planes. So all the lines on the quadric surface are double lines in that case, and the structure of these double lines is really what Segre and Fano actually exploit in their paper. The most you can have, if you have a finite number of double lines, the most you can have is 6, and they form a tetrahedron, and that's another simple example of a line complex. What happens if the singularity surface isn't a quadric surface, but it's actually a tetrahedron? So then you have a singularity surface of 4 planes, and that thing can be attached to the types of quadric surfaces that Gino Loria studied in his dissertation. The tetrahedral line complexes are given by a tetrahedron, and then the family of all lines that meets its 4 planes in a fixed cross ratio. So it's easy to see, and you have then 4 planes, you need 3 parameters for each plane, so you have 12 plus 1 for the cross ratio. So there you have an example of, still very simple, these tetrahedral complexes have 13 parameters instead of 9. If you go up to that general case, you're going to have 19. So there's a lot of room in between for different types of things. So this is already, of course, getting into details a little bit, but you can't talk about the subject otherwise. Yeah, so Plucker and Klein looked at the general case, but Plucker never identified it as a Kummer surface. It's rather an odd thing. He realized that the generic quadratic line complex has a singularity surface, which is a surface of order 4 and class 4. That's exactly what you need for 16 singularities. But he never went after Kummer had published it, but he never mentions Kummer, and he never talks about the configuration of points and planes and so forth. And I suspect he just didn't know, because he'd been doing physics for 20 years and he didn't read the literature and so forth. So Klein gets to actually play that whole theme out and show how important it is for Kummer's theory. Here is Ernst Edward Kummer, who was not working in line geometry. He was working in the theory of ray systems, which are 2-parameter systems of lines, not line complexes. That mistake is sometimes made by people as brilliant as André Bay, who in his collected works of Kummer talks about Kummer surfaces and line geometry, and well, there is no line geometry in Kummer's work. There's a whole book about the Kumar surface, so if you want to know the classical theory, there's probably the place to start. And it comes from physics, it's true. It comes from the Fresnel wave surface, which, if you're interested, these early types of examples of models are hard to visualize, so if you're interested, I brought along my own special Fresnel wave surface. A colleague in Mainz, who's an expert on these sorts of things, and you'll see a few pictures of Oliver Labs here in a moment, but he also does things in glass. And if you know something about the Fresnel wave surface, you know it's really quite difficult to visualize what it looks like in different perspectives. So in the pause, you're welcome to come up and admire this object. And it's really a very, very far cry from these earlier types of models. So there's a new interest, of course, in using modern technology to produce more striking and interesting models of these classical objects. That's the first Kumar surface. The Fresnel wave surface has 16 singularities, but only 4 of them are real. The other 12 are imaginary. It's another attempt to show the inner and outer structure of the leaves on it and so forth. Difficult to see. Now, Plucker developed a whole bunch of models of his own, and this is part of the reason I want to show this, is the shift. I mean, the way people did geometry, with the real case as the central sort of thing, before the Italians, was very much about these models and so forth, and seeing things. And Plucker built a whole bunch of models himself to understand the singularity surfaces and things like this for his quadratic line complexes. Now, some of these you can find in London because he had lots of contacts with the Brits, and he gave a lecture there once, and they admired his models, and so he sent these wooden models over. You can see them in the Science Museum today. So these are singularity surfaces of special types of quadratic line complexes. And these here, in particular, the more interesting ones, because you can see that the one on the right has 8 singularities instead of 16. The one on the left has 4. And what's happening is there's a double line involved here. The Kumar surfaces have no double line, and the double line in a Plucker surface absorbs 8 of the singularities. So that's what, in effect, is happening here. Plucker made other models in zinc that are in Munich, so these are sort of private, recently taken photos of these models. This is the one with the 4 singularities, here's the one with 8, and so on. And Oliver Labs has been producing new examples of this, so I want to see if I can't get away with moving over and showing you a few pictures, because until you take plain cross-sections of these things, it's difficult to really understand their geometry. So let me just try to move over to the other stuff. So first we'll take a bunch of planes through that double line, and we'll try to anyway. So these are horizontal planes going through the double line, and what are you seeing all along the way? You're just seeing conic sections or degenerate conic sections. Now it's a quartic surface, so you should be seeing a 4-degree curve, but it's going through the double line, and that's what accounts for the fact that it's only a conic here. And the double line is at infinity, so these planes are all passing through that line at infinity. If I show you, however, this picture, now we'll see quartic curves. But in certain positions right there, and then here at the top, it degenerates into 2 lines and a conic. And so you have these sort of special singular situations that Plucker built into these types of surfaces. So with modern computer graphics, you can begin to kind of explain and see what in the world he was doing. And these models are pretty rare as far as I can tell. I've only found them they're in London, in Munich, and in Göttingen. As far as I know, those are the only places where these models exist anymore. And yet they tell us a lot about what geometry was like back in the good old days, when physics and this sort of hands-on approach was so important. Now let me go back to my text here. Oops. I'm sure there's a more elegant way to do this, but so I was talking about these things, and Klein, of course, was in on the ground floor of this when he studied with Plucker. So he actually made models of his own. He wasn't too satisfied with Plucker's models, and he didn't even like Plucker's approach. He wanted something like deformation theory, a way to get from one type to another. And so he has other models built. One of them looks like that. You can see that's like a Kummer surface, so he started with that and then worked over to other types of Plucker surfaces from there. And basically that idea that you absorb the double lines, this comes from a picture Klein drew for his collected works. Here you have 8 real points here on a Kummer surface, and they are about to get absorbed into a Plucker surface. And so that's the sort of type of thing he was trying to do. And you get the models that maybe look like that to explain it. Okay, so the classification of these things began with Klein and then his student Weiler, and it was picked up then by Gino Loria and Segre. And that's kind of the part of the transition that takes place. Klein's the first to really apply algebraic techniques and so forth, including Weierstrass's theory of elementary divisors to get going. He also notices that Bartolini's canonical form is not general enough. It only has 17 parameters instead of 19. And that's why he goes over to that diagonalized type with the x coordinates instead. And so you get this type of thing that he then launched. But he didn't go anywhere with it, really. He just took the most general case, where the eigenvalues are all distinct, mentions the other cases, and then leaves it to his student Weiler to work them out. And he does. In his dissertation, he gets like 49 different cases published in Nationale. And this is what Loria and Segre read, refine, and in effect they show it's full of errors and so forth. And that you could only do, of course, by doing very detailed work. And so this is the story of these harmonic quadratic complexes, which began with Bartolini. Then Ascieri discovers that the Bartolini complexes are simply harmonic, and that you have 2 quadratic surfaces and lines that meet them harmonically. That's the definition, essentially. And they take that concept and go with it and classify everything all over again that Weiler did, and find a bunch of refinements, etc. They also noticed along the way that Hurst had found errors in Weiler's work. Klein knew nothing about this. So when you read these letters, then you see Segre is informing him that the state of the art here is not what it should be. And that's really what explains how this relationship, these publications get going. So Segre tells him about the mistakes that Hurst found. And this is this other letter here then, where he's pointing out the errors. Even more significant, the errors where the singularity surface is a double quadrant. And he says, this is like, there's too much here, I'm not going to just write something refuting it all, so I'm going to write a new paper. That's the second paper he submits. It's about this topic, in which in footnotes he refutes or corrects the errors that Weiler had made. This could have been quite an embarrassing situation for Felix Klein. After all, he his doctoral student, and it's his topic. But Segre found all of these mistakes. He also put him in touch with Carl Rowe, Klein did, so that's a student, a very important student of Klein, who worked on quartic surfaces, and they begin corresponding. And so you have the beginning of a rich bunch of studies on quartics and related things. And Rowe had this beautiful idea. Here's the double quadratic again. And you see, you take 4 lines out of each ruling, and these 4x4 lines meet in 16 points. Well, that's rather reminiscent of a Kummer surface configuration, right? I've got 16 points here. And what Rowe showed was I can start with a Kummer surface and take any of its 16 nodes and move through space and deform to that gadget right there. I can go right back down to that. So this is my final little thing, just to connect to Segre here. In the second paper, Segre is talking about exactly this type of singularity surface. And you can tell that Felix Klein appreciated very much what Segre had to say about it, because in his own collected works, he explains how essentially starting with the surface, Segre was able to show how you get different types of line complexes with that surface. So you take 4 generators on the surface, and you take any plane, that's arbitrary, it meets the 4 generators in 4 points, A, B, C, and D. So at those points, which are going to be your singular points, you just look at tangents to those points. Those 4 lines, L1 through L4, are going to meet the surface in a second point. And so at those points, there's the kind of picture that goes with it. It meets then at 4 other points, E, F, G, and H. And at those points, you can then define a conic that goes through the first 4, and that the others are going to have tangents at the other 4 points. And then you just move to another plane, just move through the complex and keep that figure invariant, and there you have, in effect, built yourself a line complex with exactly that singularity surface. Well, I had read that years ago in Klein's collected works with a reference to Segre. His collected works are quite full of references to Segre. And I read that and kind of wondered and so forth, and now it kind of clicks. Well, yeah, that first paper that Segre wrote about this topic has exactly this in it. And so now Klein's an old man at this point. He's much older than that portrait, in fact, when he does his collected works, 1919, 1921, when he wrote about this. And I think he was very inspired by Segre to take up this early research. In his collected works, he has to do it all over again, and so on. And so you can see references to Segre's work. You can see this construction that I just alluded to here appears in the second volume. And he even thinks of a way to deform that figure in order to get back to the general case. So he's still thinking about this mathematics that Segre was doing back in the 1880s. And anyway, I conclude by saying, surely you could think of no higher praise for the fertility of Segre's methods than to see Klein still thinking about it as an old man. Thank you very much.